Have you ever felt like you're just, drowning in information? You've got maybe a dozen browser tabs open, each one screaming for your attention, just overflowing with details about some topic you really need to wrap your head around.
Oh, absolutely.
You want to be genuinely well-informed,
Yeah.
quickly and thoroughly, but without that feeling of being completely overwhelmed by just the sheer volume of it all.
That's the exact problem we try to tackle here on the deep dive. We take that stack of articles, that research, maybe your own notes, basically, your entire knowledge base on a subject, and we distill it down. We get to the most important nuggets of knowledge, the really insightful takeaways.
Yeah.
Think of us as your expert guides, helping you navigate these complex topics, maybe uncover some surprising facts, and get straight to those satisfying aha moments that really make knowledge stick.
And today we are taking a foundational deep dive into TypeScript. Our mission for this particular deep dive is, well, to guide you through those crucial initial steps, setting up a solid development environment first. Then we'll unravel the mysteries of TypeScript's basic types. Understand how TypeScript intelligently infers types, which is pretty cool.
It really is.
We'll distinguish between those sometimes confusing any and unknown types, and finally explore how to structure your data effectively using arrays, tuples, and enums. This isn't just about learning syntax, it's your essential shortcut, hopefully, to grasping the core building blocks of TypeScript, making sure you don't just feel informed, but actually empowered to start building.
Sounds like a plan. So let's roll up our sleeves and start right at the very beginning, establishing that solid foundation with your TypeScript environment.
Okay, let's unpack this then. Why does a well-configured development environment actually matter so much when you're just starting out with TypeScript? I mean, it sounds like a pretty straightforward first step, but our sources really emphasize how absolutely crucial it is.
It's the absolute first step for a really fundamental reason. Imagine trying to bake, I don't know, a complex multi-layered cake, but without the right kitchen tools, or maybe worse, with tools that are broken or just not calibrated right.
Right, disaster waiting to happen.
Exactly. You'd likely make a huge mess, waste ingredients, end up with something, well, inedible. In the software development world, a meticulously configured environment isn't just a nice to have, it actively streamlines your entire process. It's really about leveraging TypeScript's full potential for static analysis, for type safety.
Okay.
This means catching errors early, often before you even hit save or try to run your code. And that saves you immense debugging time down the line. It also dramatically improves code readability, making it easier for you, maybe your teammates, to understand what's going on. And ultimately, it significantly enhances your overall efficiency as a developer. Without this solid setup, you simply can't tap into TypeScript's powerful tooling and that proactive error prevention it offers.
That makes perfect sense. It's like setting the stage for success, right? Or maybe ensuring your oven is preheated and your ingredients are all prepped before you even think about mixing the batter. So the first actual step our sources point to is installing Node.js, and then a package manager like NPM or maybe Yarn or PNPM. What's the core role of Node.js in this whole picture?
Node.js provides the runtime environment. Think of it as the engine, basically, that allows JavaScript and, by extension, all those command line tools built with JavaScript, which are truly essential for modern TypeScript development to run directly on your computer outside of a web browser.
Yep.
It's the foundational platform. It's what your package managers and the TypeScript compiler itself operate on top of. It provides those core capabilities for executing all the build scripts and development tools you'll inevitably be using.
Understood. And for installing Node.js, the source recommends going to their official website, nodejs.org, and downloading the LTS version. Why LTS specifically? What's the thinking there?
LTS stands for long-term support. It's really the recommended version for stability, for reliability. These versions are maintained for a significantly longer period. They receive critical bug fixes, performance improvements, and crucially important security updates.
Oh.
This translates directly into less unexpected breakage for you in your day-to-day development work and just a more stable base for all your projects. Once you've downloaded the right installer for your operating system, you just run it like any other piece of software. A quick note, though, for Windows users. Sometimes, after installation, you might need a system restart for everything to be properly configured and accessible from your command line or terminal.
Good tip. And how do you verify it's all installed correctly and ready to go?
After the installation, it's really important to open a new terminal or command prompt window. That ensures your system's path variables, the things that tell your computer where to find programs, are updated.
Got it.
Then simply type node-v and also npm-tev. You should see version numbers printed out for both, confirming that both Node.js and its bundled package manager, NPM, are correctly installed and available for you to use.
Now, about NPM, Yarn, and PNPM. You mentioned NPM comes bundled with Node.js, but then we have these popular alternatives. Why might a developer choose Yarn or PNPM over NPM, especially if NPM is already there?
Well, NPM is perfectly capable, it's widely used, but Yarn and PNPM have definitely gained popularity because they offer some compelling advantages, primarily around performance and efficiency.
Okay.
They often boast significantly faster installation times, which can really add up, especially in larger projects with lots of dependencies. More importantly, perhaps, they offer more efficient disk space usage because of how they handle package caching and linking.
How so?
Well, for instance, PNPM takes this really innovative approach. It creates a single global store for all your installed packages on your machine, and then it cleverly symlinks them into your project's node modules folder.
Wow, like shortcuts.
Exactly like shortcuts. This is incredibly efficient for disk space, particularly if you have many projects using the same dependencies, because they all just share that single cached version instead of duplicating it everywhere.
So it's like a smarter way of managing your project's ingredients list, maybe. Instead of having a separate bag of sugar for every single recipe you make, you have one big shared sugar bin, and you just portion it out as needed. But that makes a lot of sense for resource management.
Precisely. That's a great analogy. And the clear advice from our sources on this is pick one NPM, Yarn, or PNPM and just stick with it for consistency across your projects.
Right.
This avoids potential conflicts, makes dependency management much smoother, much more predictable, especially if you're working within a team.
Okay, makes sense. Consistency is key.
Right.
So Node.js and a package manager are sorted. The next big step is installing the TypeScript compiler itself, TSC. This sounds like the core engine for all things TypeScript.
It absolutely is the heart of your TypeScript workflow. TSC is the core tool that makes TypeScript possible. You see, your web browser or your Node.js runtime environment, they can't directly execute your TypeScript files, the .ts files.
Right.
What TSC does is it takes your human-readable TypeScript code, it rigorously checks it for type errors. That's its primary superpower, really. And then if everything checks out, it converts, or the technical term is transpiles, that code into standard JavaScript JS files. And those JavaScript files can then be readily executed by any standard JavaScript runtime, like a browser or Node.js. You install it globally, usually with npm install daisy TypeScript. Making it global means the TSC command is available anywhere in your terminal, letting you compile your projects from any directory.
Okay, the environment's set up, the compiler's installed. Now for tsconfig.json, our sources refer to it as the project settings or maybe the rulebook. How do we actually get this file, and what's its main purpose in a TypeScript project?
Right. So you start by creating a new directory for your project. msevdir my TypeScript project. Then you navigate into it with cd my TypeScript project.
Standard stuff.
Yep. Inside that directory, you run tsc init. This command automatically generates a default tsconfig.json file for you, and it's pre-populated with a bunch of common compiler options, many commented out initially. This file truly is your project's control center for TypeScript. It's where you tell the TSC compiler precisely how to behave. Things like, what version of JavaScript should it target for compatibility? How should modules be handled? Where are your source files located? Where should it put the compiled JavaScript output? And crucially, how strictly should TypeScript enforce its powerful type checking rules? It basically dictates the entire compilation process.
So it's not just about compiling the code, it's about how it compiles, what rules it follows, and even where your project files live and where the output goes. Let's break down some of the most impactful options within tsconfig.json. Our sources gave a helpful example snippet.
Absolutely. Let's look at a fairly common configuration you might see. Compiler options, target, ES2020, module, common.js, outdir.rootdir.src, source map to true, strict true, as module interop true, force consistent casing in file names, true, force consistent casing file names include encode not src, no modules cut. Okay, first off, compiler options is the main section, the heart of the file, where most of the configuration magic happens.
Right.
Target ES2020. This is a critical setting. It tells TypeScript to compile your code down to ECMAScript 2020 syntax. Why does this matter? Well, compatibility. If your code needs to run in older browsers that don't support modern JavaScript features, you might target something older, like ES5.
Okay.
But for modern environments, Node.js or modern browsers, ES 2020 or even ES Next is excellent. It lets you write code using the newest JavaScript features, and TypeScript handles the necessary down compilation for you.
Got it. And module?
Module. CommonJS. This defines the module system for your compiled JavaScript output. CommonJS is the standard you'll typically use for Node.js environments. If you're building primarily for a browser and using modern module loaders, you might choose ES Next or ES 2015. This dictates how your import and export statements will ultimately behave in the compiled JavaScript files. It's sort of like choosing the right language dialect for how your code modules talk to each other.
Makes sense. Outdir and rootdir seem pretty self-explanatory. Output and source directories.
Exactly. Outdir.dist specifies the output directory where your compiled JavaScript files will land. Using dist, short for distribution, is a very common convention. And conversely, rootdir.src tells the compiler where your TypeScript source files, .ts files, are located. Keeping your primary source code in a SRC folder is also a widely adopted convention. It creates a really clear separation between your source and your compiled output.
Nice and tidy. Okay, source map true. You called this a lifesaver earlier. Why is it so important for debugging?
Oh, it's a true debugging lifesaver. When you set this to true, TypeScript generates these extra .map files alongside your compiled JS files. These source maps create a bridge, basically. They allow your browser's debugger or your IDE's debugger to map the compiled JavaScript code back to your original TypeScript code. This means you can set breakpoints, inspect variables, step through code directly in the .ts files you actually wrote, rather than trying to decipher the potentially unfamiliar transpiled JavaScript.
That's incredibly useful. Debugging compiled JavaScript when you wrote TypeScript sounds like an absolute nightmare otherwise.
It absolutely can be, yeah. Source map makes it pretty much seamless. Next, and this is a big one, strict true. This option is highly, highly recommended.
Why so strongly recommended?
Enabling strict mode effectively turns on a whole suite of strict type checking options within TypeScript. It's like your ultimate safety net. It catches a multitude of common errors really early in the development cycle, significantly improving your code quality and reliability. Think of it as turning on all the best safety features in your car. ABS, airbags, traction control. It might feel a little more restrictive initially, but it prevents far more significant problems down the road.
Great analogy. What about as module interop? True.
This option enables better interoperability between the older CommonJS module style and the newer ES modules. It specifically helps resolve some common import issues, especially when you're trying to import older CommonJS style modules into a modern ES module-focused TypeScript project. It just smooths out those sometimes tricky import scenarios, makes things work together more nicely.
Okay, handles those compatibility wrinkles.
Yeah.
And force consistent casing in file names. True. Scene specific.
It is, but useful. This option enforces consistent casing in file paths when you import modules. This is particularly helpful for cross-platform development because different operating systems like Windows, macOS, Linux handle file path casing differently.
Ah, right. Windows isn't case sensitive for file names, but others are.
Exactly. This setting helps avoid subtle bugs that might only show up when your code runs on a different operating system or in a different environment, like your CI/CD pipeline. It ensures your imports and references are always correct, regardless of the underlying file system's case sensitivity.
So it's about making sure your code works the same way everywhere, avoiding those annoying, well, it works on my machine issues.
Precisely.
Right.
And finally, outside of the compiler options block, you usually have include and exclude.
Right.
Include.src. This array tells TypeScript which file patterns it should actually include when compiling. Here, src is a common wildcard pattern that means include all files and all subdirectories within this src folder. This tells the compiler exactly where your project's source code lives.
And exclude does the opposite.
Exclude Node modules. This array specifies file patterns to ignore during compilation. Node modules is almost universally excluded because those are all your third-party libraries. They're typically already compiled JavaScript, and you definitely don't want TypeScript trying to recompile them. That would be a huge waste of time and could potentially even introduce errors.
Wow, that's a tremendous amount of control packed into just one configuration file. It really is the project's rulebook. Now, once all that's set up, what about the actual code editor you write your code in? Does it matter which one you use?
A good code editor is, well, absolutely non-negotiable for productivity in TypeScript. While you have options like Sublime Text or Atom, Visual Studio Code, or VS Code as it's commonly known, is overwhelmingly recommended for TypeScript development.
Why VS Code specifically?
Well, it's developed by Microsoft, the same company behind TypeScript itself, so it has exceptional built-in support right out of the box that other editors often need extensions to even come close to matching.
What kind of integrated support does VS Code offer for TypeScript that makes it such a strong recommendation? What do you get immediately?
It's truly fantastic. Right away, you get excellent syntax highlighting, which colors your code, making it immensely easier to read and understand. Crucially, it provides powerful IntelliSense.
IntelliSense.
Yeah, that's the smart code completion as you type, helpful parameter hints for functions showing you what arguments they expect, and quick information pop-ups telling you the type of a variable when you just hover over it.
Nice.
It also offers real-time error checking and warnings directly in your editor as you type. It has integrated debugging capabilities and powerful refactoring tools that let you easily rename variables or extract code into functions across your entire code base with confidence. It's like having an incredibly smart co-pilot guiding your every keystroke.
That sounds like it significantly boosts the whole development experience.
Yeah.
Are there any recommended extensions that can supercharge VS Code even further, specifically for TypeScript work?
Absolutely. Our sources highlight a few key categories that really enhance your workflow.
Like what?
First, linters like ESLint. These are pretty much essential for identifying stylistic issues and potential errors in both your JavaScript and TypeScript UMD. They help ensure you're adhering to quality standards and best practices.
Okay, code quality police.
Kind of, yeah. Then you have formatters like Prettier. These automatically reformat your code to maintain a consistent style indentation, spacing, line breaks, all that stuff. Saves you from tedious manual fixes and ensures your entire team's code looks uniform.
Ah, consistency again.
Definitely. Editor config for VS Code is another one. This extension helps maintain consistent coding styles across different editors and IDEs within a team. It reads a small .editor config file where you define settings like indentation style or line endings.
Got it.
And finally, IntelliSense extensions for modules and paths. Things like npm IntelliSense help autocomplete npm module names when you're writing import statements, and Path IntelliSense does the same for file paths within your project. They just drastically speed up development by reducing typing and potential typos.
So these are like extra power tools that ensure your code not only works correctly, but also looks clean, consistent, and they help you type faster. And our sources mentioned configuring VS Code settings for automated formatting and linting.
Yes, and this is where the editor really starts doing the heavy lifting for you. You can set editor.format on save, true in your VS Code settings JSON file.
Ah, format automatically when I save.
Exactly. Every time you hit save, Prettier, if you set it as default, cleans up your code formatting instantly. You pair that with editor.defaultFormatter, sbennp.prettier-vscode to tell VS Code to use Prettier for that formatting.
Okay.
And for linting, you configure ESLint using slint.validate and check your JavaScript, JavaScript React, TypeScript, and TypeScript React files. The profound so what here, the real benefit is that this entire setup catches issues as you type. It's like having an incredibly vigilant proofreader and style guide looking over your shoulder constantly. It makes your development process much smoother, way more efficient, and significantly less error-prone.
That truly sounds like a game changer for productivity.
Yeah.
Right, the environment is configured, the editor is ready to go. Now let's actually write our very first TypeScript file and compile it, completing that initial loop.
Okay, perfect. For this, just create a new file named index.ts inside that src directory we set up in tsconfig.json.
Got it, srcindex.ts.
And add this simple function .typescript.
String.return.
Hello, like string?
Greet, TypeScript, talkconsole.log, message.
So what we have here is a basic function named greet. Notice the .string after name, that's a type annotation saying the name parameter must be a string. And the string after the parentheses says this function must return a string.
Okay, explicit types there.
Yep. Then we call this function with the string TypeScript, store the result in a constant message, which we've also explicitly typed as string, though TypeScript could infer this one. And finally, we log that resulting message to the console.
Makes sense. How do we compile it?
Simple. Just open your terminal, make sure you're in your project's root directory, the one with tsconfig.json, and run the command tsc. Just tsc. Based on your tsconfig.json settings, specifically rootdir and outdir, this command will find your srcindex.ts file, check it for type errors, and if everything is okay, it will compile it into distindex.js.
Ah, into the dist folder we specified.
Exactly.
Oh.
And if you enabled sourcemap.true in your config, you'll also get a distindex.js.map file generated alongside it.
So the core cycle is clear then. You write your TypeScript code, the compiler immediately checks it against the types you've defined or inferred, and then it compiles it into runnable JavaScript. That's the fundamental loop you'll be repeating as you build.
Exactly right. That's the core workflow. And with that robust environment now firmly established, you're perfectly positioned to dive into the real building blocks of TypeScript, its types.
Speaking of building blocks, let's talk about TypeScript's core identity types. Our sources really drive home that understanding these basic types isn't just important, it's absolutely fundamental. For someone perhaps coming from JavaScript, why is this focus on types so crucial in TypeScript? Because at its very heart, TypeScript is all about types. They are the bedrock, the absolute foundation upon which everything else in TypeScript is built. If you don't grasp these basic types, you really can't effectively leverage TypeScript's immense power.
Okay.
These types enable the compiler to perform its vital static analysis, its type checking. That's what prevents entire classes of errors before your code even runs, often like we said, before you even save the file. These primitives aren't just isolated concepts either. They're the foundational elements you'll use to build all the more complex types like objects, functions, advanced data structures. Mastering them early significantly reduces debugging time, leads to far more robust, predictable, and maintainable code, and honestly just a more pleasant development experience overall.
So what are these primitive types that form TypeScript's bedrock? Let's dive into the specifics, especially maybe highlighting differences or nuances for those coming from a JavaScript background.
Right. TypeScript offers a set of basic primitive types that will look very familiar if you know JavaScript, but now with that added layer of explicit type checking, we're talking number, string, Boolean, null, undefined, and then some less common but still important ones, symbol and bigint. And finally, there's the very general object type.
Let's start with number. How does TypeScript's number type compare to what we know from JavaScript? Is it exactly the same?
It directly corresponds to JavaScript's number type, yes. This means it represents all numeric values, whether they look like integers, whole numbers, or floating point numbers, decimals. What's interesting, and sometimes a point of confusion for folks coming from languages like Java or C#, is that unlike those languages, TypeScript doesn't have separate types like int or float. All numeric values in TypeScript, just like in JavaScript, are internally treated as floating point numbers. So let age number equals 30. For an integer, or let price number, equals 99.99. For a decimal, they both just use the number type. You can also use hexadecimal literals like 0x or 00, binary like 0b1010, and octal like 0744, and they all resolve to the number type as well.
That's a good reminder about JavaScript's unique number handling. It's like in a science lab, maybe all measurements are treated as decimal numbers, even if sometimes they happen to look like neat whole numbers. What about string? Pretty standard.
String is exactly what you'd expect. It represents textual data. You get the flexibility to declare strings using single quotes, double quotes, or those incredibly useful template literals using backticks.
Right, the backticks are great.
They really are. So let first name string or let last name string, do, are standard. And you can combine them easily with a template literal. Let full name string, last name. That expression syntax inside the backticks is super powerful for embedding variables or even complex expressions directly into your strings, and TypeScript ensures the final result is, of course, a string.
And Boolean. That seems pretty straightforward, just true or false.
It is. The Boolean type represents logical values, just true or false. Simple, fundamental, absolutely essential for any kind of conditional logic in your code. Let us adult, Boolean equals true. Let a student, Boolean equals false. It's the cornerstone of decision-making.
Then we have null and undefined. These often lead to confusion or, worse, runtime errors in plain JavaScript. How does TypeScript handle these two distinct concepts, and what's the crucial safety mechanism it provides?
Right. Null and undefined are indeed two distinct types in JavaScript and TypeScript, both representing the absence of a value. Generally, undefined signifies a variable that has been declared but hasn't been assigned a value yet. Null, on the other hand, is usually an explicit assignment, indicating the intentional absence of any object value.
Okay.
Now, by default in TypeScript, null and undefined are considered subtypes of all other types, which means without any special configuration, you could assign null to a number variable, and TypeScript wouldn't complain at compile time.
Which, of course, can lead straight to those infamous cannot read property X of null or undefined is not a function.
Yeah.
Errors at runtime, the bane of many a developer's existence.
Exactly. And this is where the strict null checks compiler option becomes so incredibly important. It's part of that broader strict true flag we discussed setting in tsconfig.json. When strict null checks is enabled, and you really should enable it, null and undefined become truly distinct types. You can only assign them to variables typed as any, to their own respective types, null or undefined, or importantly, to a union type that explicitly includes them, like string null.
So you have to explicitly say this variable might be null.
Precisely. The true brilliance here isn't just having null and undefined. It's the power TypeScript gives you to decide just how strictly you want to enforce nullability. You turn on strict null checks, and suddenly those potential runtime errors, those elusive bugs that only pop up when a user does something unexpected, become compile time catches.
Right.
That's the real shift in mindset TypeScript offers. It helps you proactively find and fix these problems before they even leave your development machine, before they ever reach a user.
That's a massive safety net, a huge quality of life improvement for developers, I imagine. Okay, what about symbol? That one feels less common in everyday JavaScript compared to the others.
Symbol was introduced back in ECMAScript 2015 or ES6. It represents a unique and immutable value. The primary use case for symbols, both in TypeScript and JavaScript, is as object property keys, specifically to avoid naming collisions.
How does that work?
Every time you call the symbol function, even with the same description string, you get a brand new, completely unique value. So if you did const sim1 symbol key and const symbol key, then checking sim11 equals sim2 would actually return false.
They're truly unique identifiers.
Exactly. This makes them ideal for creating sort of private or unique object properties that, won't accidentally clash with other keys, maybe standard string keys, even if those string keys happen to have the same representation as the symbol's description. For instance, let obj says sim1 value 1, sim2 value 2, console.log obj sim1 would correctly output value 1 without any worry about sim2 interfering.
That's a very specific but potentially powerful use case for ensuring uniqueness within objects, maybe for library authors or complex state management. You also mentioned bigint.
Bigint is a newer primitive type, specifically designed to represent whole numbers larger than JavaScript's standard number type can safely handle. The standard number type has a limit, around 25 and 21.
Right, number.maxf integer.
Exactly. If you're working with extremely large integers, maybe in financial applications where you need perfect precision for very large monetary values, or perhaps in scientific computing dealing with massive data sets or calculations, bigint is precisely what you need. It allows for arbitrary precision integer arithmetic, ensuring your calculations involving very large whole numbers are accurate.
Good to know for those specific use cases. And finally, the object type. This sounds very general.
It is very general. The object type represents any non-primitive value. So basically anything that isn't a number, string, boolean, symbol, null, undefined, or bigint. This includes plain objects created with curly braces, arrays, functions, instances of classes. They all technically fall under the umbrella of the object type.
So you could write let person object name Alice, age 30.
You could, yes. Or let our batches on 2, 3. However, while the object type exists, it's generally far more useful and certainly more type safe to use specific object types or, even better, interfaces to define the precise structure of your objects.
Why is that?
Because relying on the generic object type essentially throws away most of TypeScript's type checking benefits for that structured data. TypeScript won't know about the name or age properties on your person object if you just type it as object. We'll definitely delve much deeper into interfaces in future deep dives, but for now, just know that object is the broadest non-primitive type, and usually you'll want to be much more specific for better type safety and code clarity.
That gives us a really solid grasp of the individual data types and their TypeScript nuances. But TypeScript is also incredibly smart about how it determines types, isn't it? This leads us nicely into type annotations versus type inference.
Precisely. Let's start with type annotations first.
Okay, type annotations seem straightforward. That's where you explicitly tell TypeScript what type of variable or maybe a function parameter or a function's return value should be. You use that colon type syntax like we saw earlier, let age number 3030. What's the main benefit of doing this explicitly?
The primary benefit is immediate proactive error detection. It's about clarity and safety. If you explicitly annotate a variable as, say, a number, and then later, maybe accidentally, you try to assign a string value to it, TypeScript will immediately flag that as a compile time error.
Got it.
It's like giving a very specific, clear label to a container. You're telling TypeScript exactly what kind of contents to expect. If you try to put apples into a box that's clearly labeled oranges only, TypeScript catches that mismatch right away, long before it could cause confusing problems when your program actually runs. It catches mistakes extremely early in the development cycle.
Okay, so annotations are your explicit declarations, your labels, but then there's type inference, where TypeScript often just figures it out on its own. How does that work? Its magic.
Type inference is really TypeScript's remarkable deductive reasoning at play. It's the compiler's ability to automatically deduce, or essentially guess, the type of a variable or an expression based on its surrounding context, or more commonly, the value you initially assign to it.
And the benefit? Less typing.
Exactly. The huge benefit here is that you don't always have to explicitly annotate types. This makes your code significantly more concise, cleaner, and often more readable, especially when the type is glaringly obvious from the initial value. It removes a lot of that type annotation boilerplate without actually sacrificing type safety.
Can you give us some basic examples of this inference in action? How smart is it?
Certainly. It's pretty smart in basic cases. If you write let message, hello TypeScript, TypeScript doesn't need you to explicitly add string. It looks at the value on the right, the string literal hello TypeScript, and infers that the variable message must be of type string.
Okay.
Similarly, if you write let count equals 42, TypeScript sees the number literal 42 and infers that count is of type number. And let is active true, naturally infers Boolean. TypeScript is generally smart enough to see the initial value and assign the most appropriate narrow type it can.
What about functions? Can TypeScript infer return types for functions too? That seems more complex.
Absolutely, and it's quite sophisticated here as well. TypeScript is excellent at inferring a function's return type based on the return statements inside that function. For a simple function, like function add a number, b number, return a plus b, TypeScript sees that a and b are explicitly typed as numbers. It knows the addition operator plus on two numbers results in a number, so it automatically infers that the return type of the add function is number, even though we didn't explicitly write got number after the parameters.
Okay, that's neat for simple cases. But what if a function has more complex logic? Maybe different return paths based on conditions, potentially returning different types.
That's where it gets really clever and demonstrates its power. If a function has multiple return statements that could potentially yield different types, TypeScript infers a union type.
A union type.
Yeah, a type that represents multiple possibilities combined with a pipe symbol. For example, consider this function. Function getValue flag. Flag Boolean success, return 0. Okay, it can return a string or a number. Right. Based on the Boolean flag, it might return the string success or the number 0. TypeScript intelligently analyzes both paths and infers the return type of getValue as string number. So what does this all mean for you as the developer? It means TypeScript is smart enough to comprehend these different possible outcomes and combine them into a single valid type that accurately represents all the possibilities. This ensures type safety even when you have conditional logic leading to different return types.
That's incredibly powerful for handling flexible and dynamic logic safely. Now, our sources highlight a subtle but apparently very important difference in how TypeScript infers types when using const versus let. Can you explain that distinction? It sounds quite nuanced.
It is nuanced, but it's where inference gets really interesting and can proactively prevent some unexpected errors down the line. When you declare a variable using const, TypeScript infers the most specific type possible. Often this is what's called a literal type.
A literal type, like the exact value.
Exactly. Because const variables, by definition in JavaScript and TypeScript, cannot be reassigned after their initial declaration, TypeScript knows their value will never change from that initial assignment. So for const myString hello, the inferred type isn't just the broad string type, it's the literal type hello. This means myString can only ever hold that exact string literal value hello.
And let is different because its value can be reassigned later.
Precisely. When you use let, like in let myString2 hello, TypeScript infers a broader, more general type, in this case, just string. It does this because it understands that myString2, being declared with let, could legitimately be reassigned to any other string value later in your code. For example, myString2 xworld.
Why is this distinction really interesting, as you put it?
Because this difference can prevent subtle bugs. If you intended a value to be constant and used const, TypeScript's literal type inference reinforces that intent. If you later try to compare that const variable to something expecting a general string in a way that doesn't make sense for the specific literal, or if some library expects only that literal value, TypeScript helps enforce that. It's a fantastic, proactive safety mechanism that underlines the immutability promise of const.
Okay, let's unpack this next concept then. Contextual typing. This sounds like TypeScript is really paying attention to the larger environment, the surrounding code where something is being used, almost like it's reading between the lines.
That's a great way to put it. Contextual typing is exactly that. TypeScript infers types based on the broader context in which an expression appears. It's like TypeScript understanding the conversation your code is having, and then intelligently filling in the type blanks for you. This feature is incredibly common and super useful, especially with function arguments, particularly callback functions, and also when you're working with things like array literals.
Can you give us an example of how that plays out? Maybe with something common like event listeners in a web application.
Certainly. A classic example is adding an event listener. If you write window.addEventListener, click function event, console.log event.clientx event.clientY, notice we didn't explicitly type the event parameter in the callback function.
Right.
But TypeScript is smart enough to know that the addEventListener method, when used with the event name click, specifically expects its callback function's first argument to be a mouse event object. So it automatically infers that the event parameter inside that function is of type mouse event.
Ah,
This immediately gives you type-safe access to all the properties of a mouse event, like client X and client T, with full auto-completion and type checking, without you having to explicitly write event, mouse event. It's anticipating your needs based on the API you're using.
that's incredibly intuitive and convenient. It anticipates the type of event object you'll get based just on the event name string.
Exactly. And it does similar clever things for array iterations. If you have const numbers equals 1, 2, 3, TypeScript first infers that numbers is of type number, an array of numbers.
Okay.
Then, when you use a method like forEach on it, like numbers.forEach, console.log number2, TypeScript automatically knows that the number parameter inside that forEach callback must also be a number because it's iterating over an array of numbers. Again, no need for an explicit number annotation on the callback parameter. It's wonderfully convenient and eliminates a lot of repetitive typing.
So what are the overall implications of all this type inference magic? What's the big picture here for developer using TypeScript?
There are several really key implications that profoundly impact your development experience. First, and most obviously, reduced boilerplate. Less need for explicit type annotations means your code becomes more concise, often cleaner, and generally more readable, especially when the types are self-evident from the context or the initial value. You don't have to clutter your code with redundant type declarations everywhere.
That's a huge boost to developer productivity and just makes the code look nicer.
Definitely. Second, improved code maintainability. This is a big one. If you refactor a function's implementation, say, it used to return a number, but now, after your changes, it logically returns a string TypeScript, automatically reinfers the new return type.
Okay.
This proactively catches potential errors in places where that function is used, places you might easily miss if you had manually annotated the return type and forgot to update it. Your types update dynamically with your code's logic, not against it. This makes refactoring much safer and gives you more confidence.
But there must be a potential downside, right? Can type inference ever lead to unexpected behavior if you're not careful? Maybe it infers something too narrow or too broad.
It absolutely can, yeah, if you're not mindful about how you initially declare things, especially objects. If TypeScript infers a more general type or sometimes a more specific type than you actually intended for the long run, it might inadvertently allow errors to slip through, or conversely, prevent you from doing something you intended later.
Can you give an example of that?
Sure. If you write let item name example
Oh.
and nothing else, TypeScript will infer the type as name string, a very specific object shape.
Right, just an object with a name property that's a string.
Exactly. Now, if you later try to add a new property, maybe an ID, like item.id equals 123, TypeScript will correctly throw an error. Property I does not exist on type name string item. This happens because the initial object literally only had a name property, and TypeScript inferred that precise, narrow structure based only on that initial assignment.
So if I intended to add an ID later...
Then the inference worked against you.
Okay.
In that case, you would need to explicitly guide TypeScript. You'd need to define a broader type up front, perhaps using an interface, which we'll cover later, or maybe just an inline type literal like let item.name, name.number, name, example. The let makes the id property optional, telling TypeScript it's okay if it's not there initially, but it might be added later, and should be a number if present.
So inference is incredibly smart, but sometimes you still need to step in and give it more guidance, more context, especially about your long-term intentions for how an object might evolve. What are the best practices then for leveraging type inference effectively while avoiding these pitfalls?
Good question. Definitely a few key takeaways. First, use explicit type annotations when necessary. If the type isn't immediately obvious from the initialization, or crucially, if you want to enforce a specific, perhaps broader or different type than inference would guess, like our item example, definitely add the explicit annotation.
Okay.
Second, be mindful of literal types when using const. Remember that const infers the exact literal value. If you need a more general type like just string instead of hello, for a variable declared with const because maybe it needs to interact with functions expecting the broader type, you might still add an explicit string annotation to widen it.
Got it.
Third, understand and leverage contextual typing where it makes sense, like in those callback functions. Let TypeScript do the work for you when the context is clear. And finally, and this is perhaps the most important best practice related to inference, always use the no implicit any compiler option. This is usually enabled by default if you use strict async.
What does no implicit any do?
It forces you to add explicit type annotations whenever TypeScript cannot confidently infer a type on its own. If it can't figure it out, instead of silently defaulting to the dangerous any type, it gives you a compile time error forcing you to specify the type. This single option prevents accidental any types from silently creeping into your code base, which could fundamentally undermine all your type safety efforts.
That's a fantastic segue into our next topic. Any and unknown, the real wildcards of the TypeScript world. Let's start with any. Our sources rather dramatically call it a double-edged sword. Why is that?
Any is essentially TypeScript's ultimate escape hatch. A variable declared with the type any can literally hold values of any type number, string, boolean, object function, null, undefined, anything. And crucially, when you use any, TypeScript effectively turns off all type checking for that specific variable and any interactions with it.
It just stops checking.
Pretty much. It allows you to opt out of the type system entirely for that specific piece of code. Now, it can be useful in very specific, often temporary scenarios. For instance, when you're migrating a large existing JavaScript code base over to TypeScript and you don't yet have all the precise type information worked out. Or maybe when you're interacting with a third-party JavaScript library that unfortunately doesn't provide its own TypeScript type definitions.
So if I declare let dynamic value any equal 30, I can then just assign anything to it later, like dynamic value John, or dynamic value Tremio, or even dynamic value name Alice, and TypeScript won't complain at all. It just ignores its own type-checking superpowers.
Precisely. All those assignments are perfectly valid from TypeScript's perspective if the type is any. You will not raise a single warning or error at compile time. The core problem, the reason it's a double-edged sword, is that you generally want to avoid any as much as humanly possible in any new code you write, because it completely defeats the purpose of using TypeScript in the first place. By using any, you're actively opting out of the very type, safety, and static analysis features you likely adopted TypeScript for. You're essentially reintroducing the potential for all those subtle runtime errors type mismatches, calling methods that don't exist, that TypeScript was specifically designed to prevent at compile time.
It's like deliberately turning off all your car's warning lights. The check engine light, the oil pressure light. You can still drive, sure, but you're missing crucial safety information that could warn you about a breakdown or an accident before it happens. TypeScript could have warned you at compile time, but any silenced it.
That's a perfect analogy. You lose all the benefits of compile time error checking for that variable, and importantly, for any code that interacts with that any type variable. This is exactly why the unknown type was introduced later as a much, much safer alternative when you truly don't know the type of a value beforehand.
Okay, so unknown is also a wildcard. It can hold any type of value, but it's safer. How does that work differently than any? What's the catch?
With unknown, you can still assign any value to it, just like any. So let unknown value, unknown 30, or unknown value, hello, that's perfectly fine. But here's the key difference, the crucial safety mechanism. You cannot perform any operations on an unknown typed variable directly, other than maybe equality checks, without first asserting or narrowing its type.
What does that mean in practical terms, asserting or narrowing?
It means TypeScript forces you, the developer, to explicitly perform some kind of type check before you can use the value. For example, if you tried to just do console.log, unknown value plus 1, directly after assigning 30 to unknown value, TypeScript would give you a compile time error.
It wouldn't just let it pass like any would.
No, it would say something like, object is of type unknown. Unlike any, which would have just let that potentially dangerous operation pass and maybe cause a runtime error if unknown value wasn't actually a number at that moment, Unknown actively forces you to prove to TypeScript that you know what you're doing and that the operation is safe.
So how would I use unknown value if I think it's a number?
You'd have to explicitly check its type first. You'd write something like if type of unknown value equals number, console.log unknown value +1. Inside that if block, TypeScript now sees the type of check, understands that unknown value has been successfully narrowed down to the number type within this specific block, and only then is the addition operation considered valid and type safe.
I get it. Unknown is like getting a wrapped present. You know it's a present, unknown, but you don't know what kind of present it is until you unwrap it, which is like doing the type check. If type of, you wouldn't just try to plug in a wrapped present assuming it's a blender, right? You'd unwrap it first to see if it's a blender, maybe a book. This isn't just about safety. It feels like it promotes more intentional coding.
Exactly. That's the perfect way to think about it. Unknown forces you to be explicit about handling the uncertainty. It turns a potential runtime time bomb into a compile time handshake, where you say, okay, TypeScript, I understand this value might be anything, but I'm explicitly checking for the type I need right now, and I'm ready to handle it safely. This mechanism is incredibly powerful for preventing a whole host of runtime bugs related to unexpected data types and makes your code inherently more predictable and robust. Always prefer unknown over anyone when dealing with values of uncertain types.
From the wildcards, let's move to something a bit more structured and organized. Collections of data. We're talking about arrays and tuples. Let's start with arrays. What are arrays in TypeScript, and how do they perhaps enhance what we already know from regular JavaScript arrays?
In TypeScript, arrays are still those familiar ordered lists, just like you know them from JavaScript. But the crucial addition, and really the whole point of using TypeScript here, is type safety. Typically, all elements within a TypeScript array are expected and strictly enforced to be of the same type.
Homogeneous, right. All the same kind of thing.
Exactly, homogeneous. This ensures consistency within your collections. It prevents you from accidentally mixing, say, numbers and strings in an array where you only expected numbers, preventing potential errors when you later try to process the array elements.
And how do you declare them? Is the syntax different from JavaScript?
There are two main ways to declare the type, both quite straightforward. The preferred and generally more concise way is using the type syntax. For example, let numbers, number 1, 2, 3, 4, 5, or let names, string, Alice, Bob.
Okay, type followed by square brackets.
Yep. The alternative is using the generic array type syntax like let numbers, array number equals 1, 2, 3, 4, 5. Functionally, they're exactly equivalent. Most people prefer the syntax just for its brevity and readability.
And array manipulation. Do all the usual JavaScript array methods like push, pop, map, filter still work? And does TypeScript keep track of the types?
Yes, absolutely. And that's where the real benefit comes in. They work just as you'd expect from JavaScript, but now with that invaluable layer of strong type safety integrated, all your familiar methods are there.
So like push.
Push and unshift for adding elements will give you a compile time error if you try to add an element of the wrong type. For example, pushing a string into a number. Methods like pop and shift for removing elements will correctly infer the type of the returned element, for example, a number from a number, or undefined if the array might become empty, assuming you have strict null checks enabled.
And what about those powerful higher order functions like map, filter, and reduce? How does TypeScript handle those?
All fully supported and wonderfully type safe. You can still use traditional for loops, of course, but also functions like for each to execute a function for each element, knowing the element type. Map creates a new array by applying a function to each element. For example, let squared numbers odd num 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 would correctly result in squared numbers being inferred as number. Filter creates a new array containing only elements that pass a certain test, like let even numbers numbers. Filter number 2 equals 0, again correctly returning a number. And reduces the array down to a single value, such as calculating a sum. Let sum numbers dot reduce equal 8 plus cur 0. TypeScript intelligently tracks the types through all these operations, ensuring that whatever comes out is still of the expected type, or maybe a new array with the type that makes logical sense based on the transformation you performed. It helps maintain data consistency through complex manipulations.
So TypeScript really ensures that your array remains type consistent throughout its lifecycle, no matter how you manipulate it. What about arrays of arrays, like for grids or matrices, multidimensional arrays?
Yep, TypeScript fully supports those too. They're incredibly useful for representing data structures like matrices, game boards, grids, or even complex nested lists. You declare the type like this. Let matrix number 1, 2, 3, 4, 5, 6. This says matrix is an array where each element is itself an array of number. And you access elements using chain square brackets, like matrix 12, which would be 6 in this case. TypeScript will correctly infer that matrix 1 is of type number and that matrix 12 is of type number.
Finally, for arrays, our source mentions read-only array. What's that about? When would you choose to use that?
Read-only array type, or the more concise shorthand read-only type, is a way to ensure that an array cannot be modified after it's been created. It's a powerful tool for enforcing immutability for your collections.
Immutability, meaning it can't be changed.
Exactly. It prevents methods that mutate the array, like push, pop, splice, or even direct index assignment, number 0, 10, from being called on that array. TypeScript will give you a compile time error if you try.
So why use it?
If you have a list of data that should absolutely never change once it's established, think maybe historical facts, application configuration settings loaded at startup, or maybe the results of an expensive calculation that you want to protect from accidental modification, a read-only array is your safeguard. It clearly signals to TypeScript and to other developers reading your code, this data is fixed, don't let anyone change it, and the compiler actively enforces that promise.
That's a great feature for safety and architectural clarity. Now let's pivot to tuples. Our sources describe them as a special type of array that stores a fixed number of elements with known potentially different types. That potentially different part seems to be the key differentiator from regular arrays, right?
It absolutely is the defining characteristic and the fundamental difference. While standard arrays are homogeneous, meaning all elements usually share the same type, tuples are specifically designed to be heterogeneous. They allow you to define a very specific, fixed structure where each position in the sequence has a predefined type, like saying the first element must be a string, the second must be a number, and the third must be a Boolean. The position and the type of each element are rigidly enforced by TypeScript.
How do you declare a tuple then, given that strictness about order and type?
You specify the exact sequence of types for each element within square brackets in the type annotation. For example, let person, string, number, Boolean, Alice, 30, true.
Okay, a tuple is string, number, Boolean.
Right, and the order and types are strictly checked. If you tried to assign 30, Alice, true to that person variable, TypeScript would immediately throw a compile time error because the types are in the wrong order according to the tuple definition.
And element access. Is it still by numerical index, just like arrays?
Yes, access is exactly like arrays using zero-based numerical indices. So let name, string, person 0, would correctly extract Alice, and TypeScript would know that person 0 is guaranteed to be a string based on the tuple type definition. Let age number, person 1, would get 30 as a number.
Can tuples have optional elements, like maybe a field that isn't always present?
Yes, they can. You denote an optional tuple element by putting a question mark S after its type in the definition. However, there's a rule. Optional elements must appear at the end of the tuple definition. For example, let employee does string, number string, S80. This defines a tuple that must have a string and a number, and optionally might have a third element, which, if present, must be a string.
Okay, optional elements go last. What about rest elements in tuples? That sounds like it could combine fixed parts with maybe a variable trailing part.
It does exactly that. Rest elements allow you to define a tuple that has a fixed set of initial element types, followed by a variable number of elements, all of the same specific type. For instance, let line.string.number, line 1, 2, 3, 4, 5.
Ah, so the first element is definitely a string.
Right. Line 0 would be the string line, and the remaining elements signify that any subsequent elements must be numbers. You could access these remaining numbers maybe using array methods like line.slice1, which would return a number containing 1, 2, 3, 4, 5. It gives you a strong type contract for the known initial elements while allowing flexibility for trailing data of a consistent type.
Can tuples be made read-only too, just like arrays?
Yes, absolutely. You can use the read-only keyword before the tuple type definition. Let a point read-only number equal 10, 20. Just like with read-only array, TypeScript will then prevent any attempts to modify the tuple's elements after it's been created. For example, point 0 equals 5 would be an error.
So what are the common use cases for tuples? When would you typically reach for a tuple instead of maybe just a regular array or even a simple object? Where do they really shine?
Tuples truly shine in scenarios where you need to represent a collection with a fixed number of related values and where the position of each element has a specific, well-defined semantic meaning and type. They're perfect when the order of the data is intrinsically important. Common use cases include representing coordinates. A 2D point is naturally number, a 3D point number. The order, x, y, z, is crucial. Returning multiple related values from a function. Instead of creating a specific object just to return 2 or 3 related things, a function might simply return a tuple like statusCode.number, responseBody.string. It's concise and type safe, Defining data structures with a fixed schema. Think about representing a single row from a CSV file where you know the exact sequence and type of each column, like product.string, quantity.number, shipped.boolean.
Okay, so summarizing that difference again. Tuples are like a small, highly organized, multi-compartment box, maybe, where each compartment is labeled and holds a specific type of item, and you know exactly how many compartments there are and what should be in each specific slot.
That's a great analogy.
Whereas arrays are more like a single big basket that can hold many items, potentially an unknown number, but they all generally need to be of the same type, like all apples or all oranges.
Exactly.
So when might a tuple be too restrictive? When should we perhaps lean towards using an object with named properties, or maybe an interface instead?
That's an excellent design question you need to ask yourself. Tuples are fantastic when that fixed count and the positional meaning are inherent and clear, especially for just 2 or 3 elements like coordinates or simple return values. But if you start having more than a few elements in your tuple, or if the meaning of each piece of data isn't immediately obvious just from its position, then an object literal or defining an interface becomes far more readable and maintainable.
Because names are clearer than positions.
Precisely. Trying to remember what the 5th element in a tuple like string, number, string, number represents is hard. A named object like first name, string, age, member, street, string, city, dot string, state, string, zip, number is instantly understandable. So the rule of thumb is, if your multi-compartment box starts getting too many compartments and you're struggling to remember what's supposed to be in slot 5 versus slot 6, that's your cue to switch to a structure with named properties, like an object or an interface.
That's a really helpful rule of thumb for choosing the right tool for the job. Okay, that brings us to our final building block for today's deep dive. Enums, which the source describes as named constants. What exactly are enums, and why would we as developers want to use them in our TypeScript code?
Enums, short for enumerations, provide a really powerful and clear way to define a set of named constants. Essentially, they let you create a new custom type where a variable of that type can only be one of several possible predefined values that you list out. The immense benefit here is that they make your code significantly more readable, much more maintainable, and considerably less prone to certain types of errors. Instead of using ambiguous magic numbers, like if status 2, or arbitrary magic strings, if admin, scattered throughout your codebase, you use clear, meaningful names provided by the enum.
So it's kind of like creating a limited menu for certain values. You can only order predefined items from the enum list, which prevents typos or someone trying to use an invalid choice that isn't on the menu.
That's a perfect analogy. You gain compile time type safety for what would otherwise be just loose strings or numbers. It makes your intentions crystal clear to anyone reading the code, including your future self, and the compiler enforces that only valid options from the enum are used.
Let's talk about the different kinds of enums TypeScript offers, starting with numeric enums. How do they work?
Numeric enums are probably the most basic and historically the most common type. In a numeric enum, each named member is assigned a numeric value. By default, if you don't specify any values, the first member automatically gets the value 0, and each subsequent member auto-increments by 1 from there.
Can you give an example?
Sure. If you define enum direction up, down, left, right, then direction.up would correspond to the number 0 direction, down to 1, direction.left to 2, and direction right to 3. If you then wrote let move, direction.up, console.log move, the output would actually be the number 0.
But you also have the flexibility to explicitly assign numeric values yourself, right? You don't have to start at 0.
Yes, absolutely. Yeah. You can explicitly assign a number to any member. If you assign a value, any subsequent members that don't have an explicit assignment will auto-increment starting from the last explicitly assigned value plus 1. For example, enum status open 1, in progress, closed.
Ah, so open is 1.
Right. Then in progress would automatically become 2, and close would become 3. So if you had let task status, status.inprogress, console.log task status, the output would be the number 2.
Okay, that's numeric enums. What about string enums? Those sound like they might be even more readable sometimes, or maybe useful for interacting with external systems.
They often are, yes. In a string enum, each member is explicitly assigned a string literal value. They are generally considered more readable than numeric enums in many cases because the value itself directly represents the intended concept in a human-friendly format.
Like the HTTP methods example earlier.
Exactly. That's a perfect use case.
Yep.
You know, HTTP method, get, post, put, delete. It's exceptionally clear what HTTP method.get represents. It's literally the string getty. String enums are particularly useful when your enum values need to be used directly as strings, perhaps for logging meaningful messages, defining configuration values that need to be strings, or especially when interacting with APIs where specific string values are expected as parameters or returned in responses, rather than abstract numeric codes.
So HTTP method.get literally evaluates to the string getE. That's very clear and almost self-documenting. Our sources also briefly mention something called heterogeneous enums, where you might mix numeric and string values within the same enum.
Yes, while technically possible, heterogeneous enums where you mix string and numeric values are generally less common and often advised against for the sake of clarity and predictability. TypeScript does allow it, for example. Enum mixed, no. Zero, yes, yes.
Okay.
If you then used mixed, yes, its value would be the string yes, while mixed, no would be the number 0. But mixing types like this within a single enum can sometimes make the code harder to reason about. Generally, it's cleaner to stick to either purely numeric or purely string enums for better readability and maintainability.
Good advice. Now let's get into the practical side. Where do enums truly shine in real-world coding? What are the common scenarios where a developer would instinctively reach for an enum as the right tool?
Enums are incredibly versatile for defining any fixed, well-known set of related constant values. They create a common type-safe vocabulary within your codebase, making everything more robust and understandable. A very common use case is representing states.
States, like the status of something?
Exactly. Think about the different states an object or a system can be in within your application. In an e-commerce application, for example, you might have an order status enum with members like pending, processing, shipped, delivered, canceled.
Right.
This makes your code that handles orders much more robust and self-documenting. You might define an interface, like interface, order.string, status, orders, items, string, do them. Then a function to update the status could look like function of habitus. Order new status, order status.void, order.status, who of new status. Console.log, order status updated to order new status. Notice new status parameters typed as order status.
So TypeScript enforces that you can only pass in one of the valid statuses defined in the enum?
Precisely. It prevents typos like shipped, or someone trying to use an invalid status like waiting. It guarantees you're always working with known, valid states.
That's great for maintaining consistency and preventing tricky logical errors based on invalid states. What are some other common uses?
They're also perfect for defining configuration settings. Maybe an enum for environment, dev, test, prod, or for managing error codes where you give meaningful names to numeric or string error codes, making error handling logic much clearer than just dealing with raw numbers. You could also use them for representing UI elements, like different button types in a toolbar, save, open, print, where each enum member might correspond to a specific action or icon.
And the source mentioned defining API request methods, which we touched on briefly with string enums earlier. That seems like a really good fit.
Yes, that's a prime example where string enums are immensely valuable for ensuring correctness. You can guarantee that only valid HTTP methods are used when constructing and sending network requests. Imagine defining enum HTTP method get post put delete. Then you could define an interface for your API requests. Interface API request method, HTTP method url.string data.any.
Now, any function that accepts an API request object, like functions sendRequest.APIRequest.voidConsole.log, sending request.method.request.voidConsole.log, sending request.method.request to request.voidConsole.log, it provides compile time safety for your API interactions.
This raises an important question. Thinking specifically about that API methods example, how does using an enum like HTTP method make our code not just safer, but also significantly easier to understand, especially when we're collaborating with other developers on a team?
That's a great point. It fundamentally creates a shared, unambiguous vocabulary. When a new developer joins the team, or even when you yourself revisit code you wrote months ago, seeing request.method equals HTTP method.get immediately tells you the precise intent and the limited set of valid possibilities. There's no ambiguity.
Unlike seeing request.method equals get, where you might wonder, should it be lowercase get, or maybe get? Exactly. The enum eliminates all those magic strings and the potential variations or typos that come with them. It makes the code inherently self-documenting because the valid options are explicitly defined in one place, the enum definition. This drastically reduces the likelihood of typos or developers using incorrect values that could lead to subtle runtime errors or, worse, unexpected behavior on the server side because an invalid method string was sent. This level of enforced consistency and clarity is absolutely invaluable for effective collaboration and building maintainable, long-lasting software.
That makes perfect sense. It standardizes the language we use in the code. And finally, our sources mention using enums for defining things like user roles or permissions.
Absolutely. Another classic use case. You can define something like enum user role, admin, editor, viewer, IoT. Then if you have a user interface, perhaps interface username dot string role user role, you can write functions to check permissions in a very clear, explicit, and type-safe way.
How would that look?
You might have a function like .function, check permission, user required role dot Boolean return user.role, that's required role. Yeah. The types make the function's purpose unmistakable. If you have an admin user whose role property is userRole.admin, then calling check permission admin userRole.admin will correctly return true. Checking an editor user for userRole.admin will correctly return false. It's a robust and highly readable way to manage access control logic within your application, far better than using magic strings like admin or maybe role IDs like one.
Wow, okay, that's a truly comprehensive look at these fundamental building blocks of TypeScript. We've gone from setting up the entire environment to understanding the core types and these essential data structures like arrays, tuples, and enums.
Indeed. We've definitely laid a very strong and I hope much clearer foundation for working effectively with TypeScript.
So, just to recap for everyone listening, today we embarked on a foundational deep dive into TypeScript. We meticulously walked through setting up your essential development environment, ensuring you have the right tools like Node.js, TSC, and a well-configured tsconfig.json, plus a productive editor setup like VS Code so you can start writing code smoothly and efficiently. We then explored the most basic types number, string, Boolean, null, undefined, symbol, and bigint, which really form the bedrock of your code, providing that initial crucial layer of type safety and making your code more predictable from the get-go.
Then we uncovered the magic of type inference, seeing how TypeScript intelligently deduces types much of the time, keeping your code concise while still being incredibly smart about type checking. We navigated the crucial nuances between any and unknown, hopefully making it crystal clear why unknown is the far safer alternative when dealing with uncertain types, and how it forces you to write more predictable, intentionally type-checked code.
Right. And finally, we learned how to organize collections of data effectively. First, with arrays for those homogeneous lists where all elements are the same type. Then with tuples for those special fixed-length mixed type structures where the order and count really matter. And we discovered that immense power and clarity of enums for creating readable, type-safe named constants that eliminate ambiguity and prevent a whole class of errors, essentially establishing a shared, reliable language within your code base.
You've now, hopefully, grasped the essential tools and the core concepts you need to confidently start writing more robust, more predictable, type-safe TypeScript code. This deep dive into the fundamentals isn't just about learning syntax, though. It's really about encouraging a critical shift in your mindset as a developer.
A mindset shift how?
It's about starting to think proactively, anticipating potential type-related errors before they happen. It's about writing code that more clearly communicates its intent through types. And ultimately, it's about collaborating more effectively by establishing clear contracts and a common vocabulary within your code base, thanks to these foundational TypeScript features.
So a question for you listening. What stands out to you the most from this initial exploration of TypeScript's foundations? And how might this foundational knowledge empower your next coding project or learning adventure?
It's worth thinking about how these seemingly simple concepts, types, inference, basic collections really lay the groundwork for building incredibly complex, scalable, and powerful applications that are ultimately much easier and more enjoyable to build and maintain. Absolutely. And this truly is just the beginning of your TypeScript journey. We've only scratched the surface today by laying the groundwork. There are even more fascinating and powerful topics to explore in future deep dives. We'll build upon these fundamental concepts to unlock even greater potential, exploring things like interfaces, generics, advanced types, classes, and so much more, allowing you to achieve even greater power, flexibility, and safety in your code.